Hello everyone, thank you for being here today. I hope everyone is safe and sound. My name is Alec. I'm a third-year PhD student from Simon Fraser University. I'm a member of the High Excel Lab directed by Professor Fang, and I'm also part of the Reconfigurable Computing Lab directed by Professor Shannon. Today I'll be presenting our work demystifying the memory system of modern data center FPGAs for software programmers through microbenchmarking. With the end of CPU scaling due to the power and utilization walls, FPGAs have gained increasing attention in data centers as they've shown great promise for high-performance compute at a great energy efficiency. For example, back in 2014, Microsoft started the Catapult project, which focused on using custom FPGAs in their data centers. As a result, this improved the ranking throughput of the Bing search engine by 2 times while consuming only 10% more power. Today, many industry-leading cloud service providers have deployed FPGAs in their data centers for public access. Cloud FPGAs are gaining vast interest in academia and industry as they can be configured to host flexible and custom hardware accelerators for various workloads. FPGA accelerators not only can provide high-performance acceleration, but also are energy efficient thanks to the customizable accelerator design architectures. Today's cloud FPGAs typically come in a multi-die package and have multiple off-chip storage memories like DDR or even HBM. For instance, a Xilinx Alveo U280 data center FPGA shown here in the figure has 3 FPGA dies called SLR, super logic region, and has 2 DDR4 off-chip DRAMs and 2 stacks of HBM2 for storage. These give cloud FPGAs abundance of logic resources and off-chip memory bandwidth when implementing accelerators. As great as these FPGAs are, it's still quite challenging to design custom accelerators that can efficiently utilize the memory system on these FPGAs, especially for the large community of software programmers who wants to accelerate their programs using high-level synthesis. Here are some common challenges in harnessing these FPGAs off-chip bandwidth. First, if one simply feeds a CPU software program with primitive data types like int32 or 32-bit float to an HLS compiler to generate an accelerator design, typically only less than 5% of the FPGA off-chip bandwidth can be utilized. Second, the advertised bandwidth from the FPGA vendors are always higher than what can be practically achieved. Lastly, the results and tools that software programmers rely on when developing and optimizing custom accelerators, such as the HLS synthesis report and the hardware emulation, don't provide an accurate bandwidth model. These challenges are important to tackle for both designing high-performance HLS accelerator as well as for the software community to accelerate adopting HLS in their workflow. In this slide, we'll skip the details of the figures and focus looking at the performance gaps between different design configurations based on the series of key factors that we have identified. This graph shows the bandwidth trend when burst accessing different amounts of data consecutively, shown on the x-axis. The data are accessed via a single XE4 port from an off-chip DDR4 memory. Each line in the figure represents a different port width. First, for the same data size, the port width of 32-bit and 512-bit can have a 15 times performance difference when burst accessing the same amount of data. However, even with the best performing port width of 512-bit, the data burst access size may still impact the bandwidth performance by a factor of 4.6. Next, when multiple concurrent ports are used to access from the same off-chip memory, shown on the top right figure, even though all these configurations have the same total port width of 512-bit, unstable bandwidth degradation occurs as the number of ports increases. Fortunately, this unstable degradation can be prevented by carefully tuning the port maximum burst length, which is a parameter option for the HLS XE4 port. It specifies the maximum number of port width-sized values to transfer during a single burst access. More details on these figures will be explained in later slides, but because of these significant performance gaps in the FPGA memory system, we are motivated to characterize it through microbenchmarking and figure out how to achieve the optimal performance. Our goal for this work is to develop a set of open-source HLS-based microbenchmarks which software programmers can use to quantitatively evaluate how all the identified key factors introduced in the previous slide impact the bandwidth, latency, and resource usage in an HLS accelerator design. We focus two of the most commonly used memory connections in an HLS design. First, is the accelerator to off-chip memory connection via the memory-mapped AXI4 port. Second is the accelerator to accelerator connection using the AXIS streaming port. However, due to the limit of the talk, we'll focus on the bandwidth aspect of the memory-mapped AXI4 port. Please refer to our paper for more details on other results. For the rest of this talk, I'll first cover the design challenges and solution for our memory-mapped AXI4 bandwidth test. Next, I'll go over the results and insights that we've collected from the AXI4 bandwidth test. Then, using case study designs, we demonstrate how a software programmer may be able to leverage our microbenchmarking results and insights when designing and optimizing an HLS accelerator. Again, due to time limit, we'll only be discussing the KNN kernel in this talk. Lastly, I'll summarize our talk with a conclusion statement. For our microbenchmarks, we only use primitive operations such as read and write. However, several design challenges arise from this simplicity. First of all, memory access operations alone complete very quickly, especially considering the data transfer size is in kilobytes. It's difficult to measure accurate performance since we're using the host CPU timer to measure the performance. The accuracy can be affected by the latency overhead from the FPGA platform shell and other miscellaneous sources. Second, since no arithmetic operations are done on the access data, by default, HLS2 would interpret these repetitive operations as dead code during logic optimization. Lastly, when multiple ports concurrently access data from the off-chip memory using separate loops, HLS2 would schedule these access to run in sequential by default. Here, I'll walk you through a sample microbenchmark for characterizing the read bandwidth of two memory-mapped AXI4 ports. First, two input data arrays, each mapped to an AXI4 port on a unique port bundle. Second, the data type of the data array is defined as AP_int W, where W defines the port width. Third, the number of elements in the data array can be passed in as an input parameter, then later being used in the data access loops on lines 15 and 20. Note the pipeline with the initial interval 1 directive used on lines 16 and 21 indicates burst access. Last but not least, the maximum burst length option can be specified here. By default, HLS sets it as 16. To overcome the short execution time of the microbenchmark, we add an outer repeating loop to each of the memory access loops. To prevent logic optimization on highly repetitive memory access, the volatile keyword is added to both the input data arrays and the internal temporary variables. Lastly, the data flow directive is added to enable concurrent access from both ports. As evaluation, we characterize the memory system on both the DDR4-based Xilinx Alveo U200 FPGA as well as the HBM2-based Xilinx Alveo U280 FPGA. The U200 has 4 16GB DDR4 banks, and U280 has 32 HBM banks with a total capacity of 8 GB. On the software side, we used 2019.2 version of Xilinx Vitis and XRT to build our microbenchmarks, which all run 300 MHz. This is a graph showing the bandwidth trend when burst reading different amounts of consecutive data from an off-chip DDR4 memory via a single AXI4 port. On the y-axis of the graph, we have the bandwidth measured in gigabytes per second, and on the x-axis, we have the consecutive data access size in kilobytes. This line here shows the bandwidth trend of a 128-bit wide AXI4 port when burst accessing different amounts of consecutively stored data on an off-chip DDR4 memory. We can see the bandwidth increases as consecutive data transfer size increases. As more consecutive data are transferred, the more DRAM row buffer locality is leveraged, and less the impact from the DRAM access overhead. Therefore, it also improves the bandwidth performance. However, the gain plateaus at around 128 kilobytes once the locality benefits are fully leveraged. Next, for other AXI port widths, ranging from 32-bit to 1024-bit, we observe the similar trend as the 128-bit wide port. However, the peak bandwidth increases as the port width increases and plateaus at 512-bit, as it fully utilizes all the connection pins for the DDR4 memory. The peak read bandwidth measured for the DDR4 memory is around 18 gigabytes per second. Lastly, by default, the port maximum burst length is set as 16, and we see no further performance improvement when it increases. The left figure shows the achieved bandwidth when multiple Axie4 ports are used to concurrently access from the same object memory using the default HLS maximum burst length of 16. We show 3 different multi-port configurations in comparison with the previously shown single-port design in the blue line. The orange line shows a design with 2 of 256-bit ports. The gray line shows a design with 4 ports, each being 128-bit wide. And the yellow line shows a design with 8 ports, each being 64-bit wide. We see that all the designs have a total port width of 512-bit. However, unstable degradation is observed as the number of ports increases. This is mainly due to the access switching in DRAM row buffer across different Axie ports before the row buffer is fully utilized. Fortunately, after exploring a large number of memory port configurations, we have found this performance degradation can be prevented by increasing the maximum burst length value to increase the DRAM row buffer locality. This figure shows the maximum effective bandwidth can be achieved for all memory port configurations when using the maximum max burst length value of 256. However, according to the Axie buffer size equation, using the maximum max burst length value can bring a significant overuse in the FPGA VRAM resource. So the begging question here becomes, does the port max burst length parameter always has to be set as the maximum value of 256 in order to achieve the best effective bandwidth? To find out the optimal burst length that achieves the best bandwidth while using the least amount of VRAM, we tested a full set of configurations with different maximum burst lengths and port width. Here's a read bandwidth trend of a design with 2 256-bit ports if the maximum burst size for both ports are set as 8 kilobit. That is, the product between the port width and the maximum burst length is equal to 8 kilobit. The bandwidth plateaus at around 17 gigabytes per second. When the maximum burst size is set as 16 kilobit, the bandwidth peaks at around 18 gigabytes per second. We then tested the 8 kilobit and 16 kilobit maximum burst size for both the 4-port design as well as the 8-port design. We concluded the 16 kilobit is the best maximum burst size. The reason is the DRAM row buffer size is 512 byte and the page size is 4 kilobyte. A maximum burst size of 16 kilobit is good enough to fully utilize the DRAM row buffer locality and amortize the page miss and address translation overhead. When accessing all the DDRs, each via its own dedicated Axie port, we observe the bandwidth to increase linearly as the number of DDR increases. On the U200, the ReMaximum read bandwidth we measured was around 72 gigabytes per second, and on the Alveo U280 FPGA, each HBM2 bank has a read bandwidth of 13.3 gigabytes per second, and the maximum aggregated HBM2 read bandwidth is around 422 gigabytes per second. To demonstrate how a software programmer may be able to leverage our microbenchmarking results and insights when designing and optimizing an HLS accelerator, here I present you with a case study on accelerating an HLS KNN kernel. First, KNN or KNearest Neighbors is a widely used algorithm in highly demanding applications such as similarity search and database query. Here's a quick overview of how the KNN algorithm works. Given an input query point and a set of neighboring points, the algorithm first calculates the distance of all the neighboring points to that input query point. Here, we're using the Euclidean distance as the distance metric, which has a complexity of O of n being the number of neighboring points in the search space. Next, based on the calculated distances, the top k neighbors are sorted and returned as output. Since only the top k neighbors are needed, the sorting complexity is O of n by k. Lastly, our initial software code is based on the Rodinia benchmark suite. Before moving on to the design details and optimizations, first I'll describe the high-level architecture of our KNN accelerator design. Based on the software code from Rodinia benchmark suite, the kernel has 2 function modules, distance calculation and top k sorting. The input data are read from the object memory and subsequently processed by these 2 modules. The intermediate distance results are stored on chip. To start off, our first architecture change is the buffer tiling. This optimization is to accelerate the data communication through burst access. And since the data are computed in tiles, the top k results are carried on chip across all tile buffers. Next, we will apply loop pipelining and unrolling to pipeline and parallelize the computation in distance calculation and top-case sorting. Then, we overlap the object memory access and computation using the double buffering technique so that the buffer loading, distance calculation, and top-case sorting can be spatially processed in parallel. Further, the axis port width is widened to allow higher memory bandwidth when accessing data from the object memory. Since there is no data dependency for the compute of the neighboring points, we partitioned the entire search space and distributed the workload amongst multiple Ps. Lastly, a global sorting module is implemented to sort the local top case from all Ps. Next, I'll go over our performance models and show how we leveraged our MicroBenchmark insights when designing our accelerator. To guide the design space exploration, we formulated a performance model to calculate the latencies and cycles for the three main tasks shown in the previous slide. The latencies are calculated based on the number of loop iteration, the initial interval of the loop pipeline, and the depth of a single loop iteration. Next, we leverage our MicroBenchmark results and adjust the Vivado HLS reported cycle latency to accurately reflect the bandwidth performance under all four of our identified parameters. Although we have developed a performance model for this case study, which can guide us to find the balanced function ratios, in practice, however, it's not always achievable, especially for compute-bound algorithms. Here, we limit the resource to a single SLR and a single DDR4 on the Alveo U200 and show 4 unbalanced designs. We show that even for unbalanced designs, using our insights can still achieve performance speedups. First, here's the design configurations and results in terms of resource usage and execution time for the baseline design, which has 14 PEs. This is the maximum number of PEs that can be connected to a single DDR. Each PE uses a small tile buffer of 1 kilobyte and a 32-bit AXI port with a default port maximum burst length value. Second, in the aggressive design, each PE has a much larger buffer size and a wider port width. In fact, these are the peak configurations for achieving the optimal bandwidth for a single AXI4 port. A 2.6 times speedup is achieved for this design since the performance bottleneck has shifted from the memory bandwidth to compute. However, this design requires a much higher number of BRAMs, almost all BRAMs of an SLR, thus only 11 Ps can be instantiated. Lastly, our optimal design is selected using the performance model, which has a closer gap between the data communication and computation. This design achieves a much higher speedup of 3.5 times while requiring less resource than the aggressive design. For both the aggressive and optimal design, the maximum burst length is set so that the maximum burst size is 16 kilobit. To validate the importance of this parameter, we also show a performance of a suboptimal design, which is exactly the same as the optimal design, but with a default maximum burst length of 16. The result shows that there's nearly 1.2 times improvement over the baseline design, and this confirms our microbenchmarking results. If you're interested in knowing more about this KNN accelerator design, please check out our FPT 2020 chip KNN paper. To sum up, in this work we provide quantitative evaluations for the performance of cloud FPGA memory systems. Here are the insights we covered in this talk for the object memory bandwidth performance of the AXI4 port. For accessing a single object memory using a single AXI4 port, memory bandwidth increases when the AXI port width and consecutive data access size increase. The optimal bandwidth peaks when port width becomes 512-bit wide and data access size goes beyond 128 kilobytes. On the other hand, when a single object memory is being concurrently accessed by multiple AXI ports, the bandwidth performance unstably decreases due to DRAM row buffer switching. Nevertheless, we found this performance degradation can be fixed by adjusting the maximum burst length parameter for each AXI port to have a 16 kilobit of maximum burst size per access. We've also open sourced our HLS microbenchmarks used in this work. Lastly, we presented 2 case studies to demonstrate how to leverage our microbenchmark insights when designing HLS accelerators. Finally, I'd like to thank our sponsors for funding this work, and here is the link to the source of our microbenchmarks and case study designs. Thank you for your attention.